Another reason why the unit step function is so important is because it's going to be your digital signal. And if we go to Desmos and from the previous lesson, we defined our unit step function, and let's build a signal that's 1 second wide, and it'll just be a digital pulse like that. So it's basically just a step function, and at some time it's terminated. This could be, you could do 0.001. Let us zoom in here. Yeah, that's not very wide at all. So this can be your mathematical description of a digital pulse. That's about 1 kilohertz. So this is the step function is a good way to mathematically kind of describe a digital pulse or some kind of input. And we can build a full digital signal if we want, an 8-bit message. And let's go over to the whiteboard. On the left, I've drawn a digital, so we go 1, 2, 3, 4, 5, 6, 7, 8 bits. And this is going to go into a register. So we're sending this on our line, on our transmission line. And we have a sampling frequency, so we sample, this is a 1, here is a 0, 1, 0, 1, 0. And this is what we get in our register. But then we take our oscilloscope and we zoom in on our digital signal. And we see that it's not a perfect square wave, so ideally this is what we would get. But on our scope we get something more like something like this. And that's this is called the step response. How does our system respond to a step function? And so let's say we have a transmission line here, and we're sending that pulse in. But due to inductances and capacitances of this wire, when we receive the signal at the end, we receive something that kind of looks like that. Now our receiver might still read this as a 1, but as you can see, it might also read it as a 0 if the threshold is above this dip here. So another way to draw this is system, and the input is step function. Let's just call it output. So and that's why the analysis of a step response is so important, and that's kind of what we're going to go into a little bit in the next lesson.